In the last video, we were able to come up with an expression which is essentially our area as our combined area of both the equilateral triangle and our square as a function of where we make the cut, as a function of x. And so now we're ready to optimize, to figure out the x that gives us the minimum combined area of these two things. So let's figure out where we might have a minimum point. And to figure out the candidate minimum points, we have to find the critical points. And to find the critical points, we have to figure out where the derivative of our function, might be equal to 0 or might be undefined. So let's take the derivative here. The derivative, let's see, the power rule, it's going to be 2 times all of this business times x. So it's going to be 2 times this, which is going to be square root of 3 over 9 plus 1 over 8 times x minus 25 over 2, which I can just write as 12.5, minus 12.5 is the derivative. Now this is going to be defined for any x. So let's think about when it might be equal to 0 to find the critical points. So let's think about, and I will do this in yellow, when does square root of 3 over 9 plus 1/8 times x minus 12.5 equals 0. Well, you could add 12.5 to both sides, and you get square root of 3 over 9 plus 1/8 times x is equal to 12.5. Divide both sides by all of this hairiness, and you get x is equal to 12.5 over square root of 3 over 9 plus 1 over 8. And I will use a calculator to figure out what this is roughly equal to. So let's turn on our calculator, and we get 12.5 divided by the square root of 3 divided by 9 plus 1 divided by 8. And the order of operations should make everything work out right over here. And then, oh, I wrote 11.5. That's no good. So let me make this a 12.5. Let's see, so I have 12.5 divided by square root of 3 over 9 plus 1/8. Now I just have to put the closing parentheses, and I get 39.38. So this is approximately equal to 39.38. Now, we don't know if this is a minimum point or a maximum point. We could try to test it out, et cetera, et cetera. We could graph it. But the easiest way to do it analytically is to just do the second derivative test. Is our function concave upwards or concave downwards, or neither at this point right over here? So let's take our second derivative. So the second derivative, which I will do in blue, the second derivative of our area as a function of x is just going to be equal to this stuff. Square root of 3 over 9 plus 1/8. So our second derivative for any x, the second derivative of this is just 0. So the second derivative for any x is going to be positive. So this is always going to be greater than 0. So for any x that we're dealing with, we have a positive second derivative, so it's concave upwards. Concave upwards. So our function looks like this. Our function looks something like this. So if we found the x value where our slope is 0, where our derivative is 0, we indeed found an x value at which our function takes on a minimum point. This is a minimum point. So there you have it. We have answered the question. Where do we make the cut? We make the cut at x is equal to 39.38. And so this length will be 39.38 for our triangle, and then the length for our square is going to be 100 minus that. And if you wanted to figure out what that minimum combined area is, you could just substitute back into this hairy expression.